Thank you, Valerio. I would like to thank all the organizers for this chance to present what we do in Africa. This presentation, there will be more focus on infrastructure, not really science, but it will be a kind of continuum to what Michel's presented, and then we would say that there is something happening in Africa. And in my title, the title of the presentation, there is Agri-Food Systems, and it's nice to see soya with wheat here, a wheat-based system that I always defended because I'm working on legumes, basically. 3 years ago, we got funding to build high-throughput phenotyping, but let me tell you that it was not easy. Why? And I think my colleagues, breeders, they know it is not easy to bring a physiologist with a breeder to work together. It was mentioned by Michel. Physiologists, they are always, centric when it comes to plant evaluation. And I will come to that afterwards when I will talking about the phenotyping platform. This was presented by my colleague Michel. And you can see that most of, the phenotyping platforms are in the global north. I don't like to say that there is nothing in Africa because there is many things happening in Africa. But if we look to those phenotyping platforms in the global north, they are basically and mostly indoor systems. And as a breeder, when you develop the technology in indoor system, when I talk about technology is variety, there is big challenge to bring it to the farmer field with all the challenges in the farmer field. Either it is in Europe, in the global north with these, intensive production, or in Africa. So we thought about developing something that should be in between. It is not the field, but it is not the controlled conditions. It is what we use it to say, and then this is the name that we choose for the platform, a closed-to-field phenotyping platform. So this platform is almost 1 hectare platform with many components. One of the things that I need to mention is that it is not a PVC tube where you evaluate only one single plant representing one genotype. It is more a mini plots. What you see here is one mini plot with 300 kg soil. So where we could eventually use the same practices as it is in the farmer field in terms of planting density and planting protocols. We have in total 1,400 mini plots. For large screening, it is a lysometric system. You can see here we are planting lentils. These are lentils of our PhD student Salma. And those are her genotypes that she selected with water-saving traits and conservation traits for under drought conditions. How it is running, this platform has basically 3 main components. There is a lysometric system robot, there is the PHENO-MOBILE, and an indoor system, which is PHENO-MARZOUG. I will go through and then present. I would like to mention that this platform is homemade. It is Moroccan-made platform. It is 95% homemade platform. All the robotic system that you will see was designed and manufactured by us with the help of a Moroccan company. The only piece that we brought from outside is this machine, which is the PHENO-MOBILE machine there. But all the other components are homemade by the team with a Moroccan company. That means we can do if we would like to do, but the only thing that can help in doing this is funding. So how it is functioning. These are, robots with 4 balances there, if you can see. These balances, they will come, take up the pot, calculate the amount of water that the plant lose through transpiration, and irrigate automatically, and then come back to the same position. So it will go and take the whitening, calculate the amount of water. Everything is automated. Just the student or the engineer, he will come to this interface, which is in the building inside, and do only all the information or put all the information related to his experiment or her experiment, and do only planting and harvesting. All in between is run with robots. The second component is this machine, this robot, which is the PHENO-MA that we bought from IFAN in France, with a with a set of sensors, basically 2 LiDAR, 1 RGB camera, a thermal camera, and spectrometer. So we have the data coming from the robot, lysometric robots, and then we have the other set of data coming from the PHENO-MA. And then this PHENO-MA also, it is fully automated. Just we link it with different sensors, Ertica terminals, and then it links a list of, or a set of satellites going from 12 to 16 satellites, and it is moving automatically, you can see here, and taking all the measurements using these different sensors from above the ground. So we have data coming from the lysometric system with whitening, calculating the transpiration. We have the other, images and sensors and signals coming from the different sensors. We combine both with other type of data that I will talking about after. This is some kind of data because we are conducting, as you can see here, an experiment. This was our first experiment using African crops. This just to stimulate a little bit Michel when he talks about African crops. So we used a kind of agroecological practices used in West Africa with millets and cowpea in terms of intercropping, and then we applied different, it's screening for different genotypes of cowpea with or without association with millets under 2 drought treatments. And then you can see here for the same pot, same genotype, how it is the behavior and the different combinations. And this is a list of traits that we collected, and then you can see here with the help of Hyphen team how we can analyze and then follow up with the different response of these genotypes or these treatments, or the full components of the experiment. Here, all the treatments that we have with all the pots, and then we chose only one to show you in response to different water treatments, the behavior in solo and in intercropping, and then you can see here how it is going with NDVA and then green cover when it comes to the pot and the crop development. As I said, we have 2, or here I would say 3 sources of data. The first one is the PHENO-MA. The second one is the lysometric robots. The third one is the weather data. Why? Because the platform, we built it in a city which is called Bengrir. Bengrir is a future scenario of climate change. We have only 150 to 100 millimeters rain a year, with a temperature that can goes up to 40, 45, but during the summer is 50 plus. A VPD that can goes up to 7, 8. We had 8 VPD this year. So that means it is the atmospheric drought. I had a discussion with colleagues from INRAE in Toulouse. They are working on sunflower, and then I told them, if you need to screen for high temperature for your sunflower, come to Morocco. What you develop in Morocco will be very useful for south of France. And this platform, and then I will come back to the network afterwards to continue with this. So we collect all the data, and then we have a supercomputer in the Mohammed VI Polytechnic University with the largest data center. So we use the data center to collect all the data, use them in these open source, softwares, to store them with the backup, and then extract, do the processing, and then visualization. Now we are working on putting in place this infrastructure. We started already with the colleagues and in collaboration with Sierra2 colleagues, so to develop the platform and make it running and use it in the next few months. This was the first, part of component of the PHENO-MA platform. Again, as a breeder, you go for, or the breeder as a physiologist, you go for large screening, you identify contrasting germplasm or genotypes, and then you need to go for, confirmation of that resistance, looking more for interesting traits or mechanisms for that specific trait. And then for this, we developed this, what we call Pheno-Marzuga. Marzuga is a region in Morocco. PHENO-MA is phenotyping. This is the V2, because we changed it a little bit with Michel. So we designed this platform, and then it was manufactured also with Mindec. How can we do with this machine? This machine, if we talk about drought, people, they directly go for drought in the soil. But there is many recent simulation studies, especially in Australia, they showed that with the climate change, it will be more the atmospheric drought. That means the drought in the atmosphere that will be more pronounced with climate change. And the normal condition is, field condition is we cannot dissociate both drought from the soil, from the drought in the atmosphere, which is the high VPD. With this machine, we can do. How? So with this machine, we can give instructions to the machine to apply some kind of, we play on the humidity and the temperature, and then we increase the temperature, we reduce the humidity, and then we increase the VPD with a peak. So the VPD is high VPD is atmospheric drought, and then with this we can, at some extent, apply a scenario of climate change or a scenario of high VPD. We irrigate very well the pots, but then we apply high VPD, high vapor pressure deficit in the atmosphere. So we can dissociate these two stresses and then see which one is more, have impact on the growth or on the behavior of that genotype. Recently, Salma, she published in JXBot publication that shows that there is two genotypes contrasting once in response to VPD. And then we were expecting to have the same behavior of these genotypes in response to soil drying. It was not the case. So the one that was resistant to high VPD was susceptible to soil drying. And there is vice versa. The other was the opposite. So that means we need to dig into that and then try to bring these two traits in the same genotype. Again, this machine is fully automated. Just you put the program and then it will be running by itself. The other component is, as a breeder also, is the speed breeding platform. Definitely to accelerate the advancement of the generations, to accelerate the genetic gain, especially in Africa, you need to have such kind of platforms. Here we do kind of crosses, and then we accelerate the breeding cycle to accelerate the genetic gain and the development of these varieties. Just these rooms, we have 150 meters square, fully controlled individually. Each table is controlled individually with two irrigation systems, fully automated using ultrasound sensors. Just you give the instruction for irrigation, it will irrigate automatically. either using irrigation by capillarity, so we put solutions here as we are part of the OCP ecosystem, or by drip irrigation. So we have these two systems for the irrigation. Also, we use, and then I will come to the next one, use this facility, especially with the speed breeding, to cluster our germplasm when it comes to the nutritional quality. So we do select high protein, high iron, high zinc from the early generation, starting from F2, F3, F4. We don't wait up to the late stage to evaluate that. So while we are conducting these accelerated generations, we do clustering, and then we cluster our material based on the traits and specific traits. So these are the three components, but we do work on not only plants, because the farmers, the consumer, is more interested, as we are too, on the final product, which is, seeds, grains. So we also establish a platform. It's a high-throughput platform also, where we use this. I will be present only these two equipments to evaluate the nutritional quality. It's more for seed characterization, more physical characterization, but also nutritional characterization when it comes to protein, iron, zinc, and other micronutrients. So we have the near-infrared spectroscopy machine, which is the FOSS, that we use to predict basically the protein, but also with the fat, with other traits or quality traits. And we do prediction because we have calibration for different, this is the last one, different crops. So we have calibration for wheat, for barley, for lentil, faba bean, chickpea, cowpea, and other, and then we are trying to develop for others. This is an optomachine that we use to characterize the morphological traits for the seed, and then recently we got this videometer for seed characterization, and also to work on a number of traits, especially when it comes to diseases and viability of seeds for germination. With this, I come to the end, and I need to acknowledge all the PHENO-MA team at UM6P. So we have here Michel with myself, but also we have Kamal, Hasna, Yunus, Salma, Marwa, Hiba, data scientist, and Nordin and Asma. This is a small team that we are building, and hopefully we are in the process of hiring many other expertise to develop internal expertise to run the full platform. Thank you very much. If there is any questions?
Yeah. We have time for one question.
No.
Hi, thanks for the talk. I liked a lot the facility you put up there, but I was wondering, when you calculate the water loss due to evapotranspiration, do you take into account the biomass gained by the CO2 assimilation in that weighting?
Very good question. And I think we discussed this yesterday with a colleague who presented on biomass. And yes, definitely, this is very interesting, because when you, do the planting, you have only seeds with a few grams, but throughout the cycle, you have the biomass production. And then what we do is we have these sensors that, especially the LiDAR, that we can reconstruct to canopy, and then we calculate at some extent the biovolume, but we translate that biovolume on biomass. And then we deduct from the weighting to calculate the exact amount of water, not taking into consideration the biomass.
Okay, so you have an idea of the density of the photosynthetic tissue, let's say, to convert volume into mass.
Definitely, because to translate the biovolume on biomass, you need to go for some kind of, calibration using a destructive method. So, and it depends on which crop. So you cannot use for example, faba bean, prediction for wheat or for maize. So you need, what we are working on is to develop a kind of calibration for each crop and also for each development stage, because when you have, the vegetative stage, it's not the same as the productive stage. It's not the same as in the maturity stage. So this is what we are doing, trying to do. It's not only that, but also the evaporation. I was expecting this kind of questions. So what we do to avoid or to minimize the evaporation, because we use like soils, is to cover with the plastic beads, like 3-4 millimeters, and then to limit this evaporation, and we have only the transpiration.
Great, thanks.
Thank you.